Whether you're looking at a galaxy or you're looking at a molecule, the problems are the same. I was interested in mathematics and physics, and I think all of a sudden I realised that you could use mathematics to actually describe the world. It was sort of the mathematical physics side of electrical engineering that attracted me. There was a professor here in physics doing some X-ray crystallography, looking at structures of molecules, and so I did some work on that as part of my PhD. There was a guy at Purdue University who was working on crystallography and DNA structure, and so I went over to Purdue University. And I was working on the sort of computational side, so I was developing computational techniques to process the data to produce images or structures of these molecules. A normal imaging situation with our eyes, for example, the light scatters off objects, passes into our eye. That diffracted or scattered light field is focused by the lens onto the retina to form an image. We use all sorts of other imaging instruments, but in many cases there's no equivalent of a lens, and so you have to collect that diffracted light field information and then process it numerically in the computer to form an image of the object. One thing I saw was a connection between imaging and phase problems in optics and in crystallography. Over the last 5 years or so, I've been applying these techniques to new X-ray sources called X-ray free electron lasers. I work on the theory and the computer algorithms that are used to process the data. We are looking at diffraction from small particles, so there's not much there. And if you look at these data frames, in fact, you might say there's nothing there. And so it's not until you average up hundreds of thousands of these frames that you actually see something. But there are other problems with these powerful X-ray sources. One is that the X-ray beam is so powerful that it immediately just obliterates the specimen. And so the other characteristic of these X-ray sources is that they produce pulses of X-rays, and these pulses are extremely brief. By the time the molecule has started to explode, the pulse has completely gone through the molecule and coming out the other side, and so it carries the information from the unperturbed molecule, a technique called diffract and destroy. These fast sources open up the possibility to do sort of high-speed movies where you get the structure, and another molecule comes along and attaches to actually watch that process by doing structures at each time point. It's all part of the enterprise of understanding how the world works, and what I'm doing is just playing a sort of a small role in a very restricted part of that enterprise. There's no shortage of interesting problems.